All right, so the last video of topic 7, equilibrium, is topic 17.1, equilibrium law. Here we are tying energetics and rates of reactions with equilibrium, the scene where all the correlations occur. So free energy. Remember, free energy is delta G, right? Gibbs free energy. So by comparing equilibrium and free energy, it helps explain why some reactions barely start and others go to completion. All right, so kind of a refresher. So if delta G is negative, that is going to tell us that the forward reaction, we're going towards products. If delta G is positive, we are working with the reverse reaction. If delta G is 0, we are truly at equilibrium. All right, and so if we have the delta G of formation equation, so delta G standard equals delta G of products minus your delta G of your reactants at equilibrium. We assume, because delta G is going to be 0, that the delta G of products is going to equal the delta G of your reactants, and that is when the reaction essentially has used up any kind of spontaneity, any kind of free energy, and it's at the lowest point of energy available. So as a reaction progresses, you're going to see a decrease in the amount of free energy as work is being done in the system. And then you're going to be increasing the entropy. So if you look at the graph, so here we have the total free energy of your reactants and products. All right, so you're seeing that decrease, so the downward slope, in total free energy as the reaction is progressing forward. And so that's the reaction, and so it's energy, work being done on the system. When you do that, you're increasing your entropy because you always move towards chaos and moving towards entropy. So as you're doing this, you're seeing an increase in your delta S. So now, in either direction, the reaction moves towards the minimum free energy, and therefore the equilibrium, at equilibrium, the net reaction stops. So at that point, so here we have our reactants, we have our products. Our delta G is negative, which means there was available energy to do work. We are seeing that as we go forward, the spontaneous reaction allows it to move forward, right? And then we hit this line, the minimum free energy. So at some point we may rocket back up a little bit depending on how much force is moving forward that reaction, but this is where then the products go back forth and break back down until you hit this low point. And at this low point, it's no longer, that is equilibrium, right? And so it is at equilibrium because there's no more, it's the lowest point of how much energy was available to do work, right? And so that is where we expect that delta G value to be at. And if you look, you're definitely a lot more towards your product side. Therefore, this mixture is going to be mostly products. Now, again, you could have started with products and you could swing back up a little bit, and it kind of swings back and forth until you have that equilibrium. So as the reaction progresses, you see a decrease in the total free energy as work is being done on the system. And you see the increase in entropy as I mentioned before. So the composition of the mixture is determined by the difference in your free energy of reactants and products, right? So if the reaction has a large delta G negative value, it's spontaneous and it's going to move mostly to products, as we saw in the previous graph. If the reaction has a large delta G positive value, it's non-spontaneous and it's going to go towards the reactants, and that's what this graph is showing you. So again, here's your total free. We are working with our reactants. Here's our products, right? And so we had very little energy to get down towards that equilibrium point where you have the minimum free energy. And you see these products, right? And these products have a huge, so even if a product was made, there's all this energy available to go back down towards that equilibrium mixture. So that gives you a very large delta G positive. So this is showing you how you can have a reaction that barely starts because you have those reactants have such a low delta G to begin with compared to the products that it's not going to move forward very much. The previous graph showed you had the reactants had a lot more reactants available and a lot more energy available to the reactants than products. Therefore, we see mostly products. So based off those delta G values, and as you saw when you go back to topic 5, and we had that list of where's that delta G value at. So if it's delta G is equal to or larger than -30 kilojoules per mole, you have, it goes almost to completion. So your free energy is going to be almost completely at products. And then we move in this direction to delta G is positive 30 kilojoules, which means we have none free energy available for that reaction. So pull those notes back out, look at this graph, and try to get yourself to understand that if this was positive 30 kilojoules per mole, negative 30 kilojoules per mole, what does that look like as you're moving towards, and how does that help determine where equilibrium is at? And so there is a mathematical relationship between Kc and delta G. And here's a calculation. Delta G equals negative RT to the natural log of Kc. This calculation is good to allow you for if reactions are too slow to reach equilibrium in a time in which we can measure it, or some components are too small to measure, like we just did with our last calculation in the last video. So all of that can be used to plug in to this equation. So let's do a sample calculation. It's essentially just some plug and chug, right? So if we have a delta G equals negative 4.38 kilojoules per mole. We have our reaction. We have CH3, COOH, plus C2H5OH makes CH3, COO, C2H5 plus water. All right. So it says calculate the value of the equilibrium constant of this reaction at 298 Kelvin. We have to use 298 Kelvin because delta G is being calculated based off standard conditions. All right, so delta G equals negative RT ln of Kc. So negative 4.38 equals negative 4.38 times 10 to the third, because the gas constant, we had to change this from kilojoules to joules because the gas constant is in joules, equals negative 8.314, 298 Kelvin times the ln of Kc. All right, so then divide by those values and you get 1.77 equals ln of Kc. So then we take E of 1.77 and you get 5.9. So that shows us that we have a negative value, right? Negative 4.38, and we have a Kc value slightly above 1. It's not large, but it's above 1. So it can tell you that you are going to move more towards the product side than the reactant side when you're at the equilibrium mixture. So now we have quantitatively shown that the negative value of delta G and the value of Kc coincide with each other. Lastly, kinetics and equilibrium. So kind of a refresher on kinetics, even though we just did this. So we have a generic equation. A plus B gives you C plus D. And this is a single bimolecular step, so one rate mechanism. So if we write our rate expression for the forward reaction, and that's going to equal K times A times B. Now remember, at the end of the kinetics, we can have the reverse reactions. So now we want to know what the rate of the reverse is. And that becomes K prime times the concentration of C times the concentration All right, so now I'm going to write our Kc expression. And so that is, your products over your reactants. Okay, so how do these two expressions relate? Well, we assume at equilibrium, the rate of that forward reaction will equal the rate of that reverse reaction. So we assume at equilibrium, K, or your forward rate expression, equals the reverse rate expression. Say that 5 times fast, right? And so when we go through and we work this out, so we say K over K prime equals the concentration of C, D over the concentration of A, B. Oh, interesting. Oh, those are the same. So that means that Kc, the equilibrium expression, equals your rate of your forward reaction divided by the rate of your reverse reaction. And so it's a ratio based off all the constants, right? So we can then base it off a ratio. So if the rate of the forward expression is greater than the rate of the reverse reaction, your Kc value is going to be large. So you're going to go towards completion. If the rate of your forward reaction is less than that of your reverse reaction, your Kc is going to be small, and it barely starts. And so now, once again, we know how to calculate rate. And based off the last video in rate, we know how to look at the inverse reaction as well. And so if we have those rate constant values, we can use those rate constant values to find out what the equilibrium constant would be to figure out where the equilibrium mixture is at. So now we've looked at where delta G is, and how do we know what value of delta G is to figure out where the equilibrium expression is going to lie. Now we can also look at rate, and if we know what the rate constants are, we can also find out where equilibrium mixture lies. And so there's so many different avenues for this all to work together. All right, so if we have a change in concentration, so now we're going back to the concepts of what affects rates. So if we have a change in concentration, so we're going to increase our reactant concentration. This is going to increase the K for our forward reaction. If we increase the K for the forward reaction, that means equilibrium is going to shift to the right towards the products because you're going to get an increased Kc value. If we increase the products, we're going to increase the rate of the reverse reaction. That means equilibrium is going to shift back towards the reactants, which means our Kc value is going to decrease, right? And so this goes back to the concept of Le Chatelier's principle. If you increase the reactants, we want to get rid of it, so you move to products. If we increase products, you want to get rid of it, so you're going to go back to reactants. And we can have that K value, right? And understanding how rate is going to be affected because now it's going to be pushed in one direction, we can now determine where the equilibrium mixture is going to lie and what that Kc can be. Now because, and ignore what I just said about Kc because we're doing concentration, Kc itself stays the same. It's the ratio, sorry, talking right at the same time, the ratio of the concentrations at equilibrium are what change, not the Kc itself. I apologize. Then we have a catalyst. So we know that when we add a catalyst, we're going to increase the rate for the forward and the rate for the reverse reaction the same. Therefore, Kc stays the same. And then, temperature. We all love temperature. So the rate of the forward and the rate of the reverse are affected by temp. We know that. Because we go back and we know K equals A e to the negative EA over RT. the Arrhenius calculation. Since temperature is there and temperature is directly related to K, you increase temperature exponentially, K changes, so on and so forth. It is an exponential relationship. All right, so if we take that understanding, if we have an endothermic reaction, the EA of the forward reaction is going to be higher than the EA of the reverse reaction. Because if we draw this for an endo reaction, we have to use a lot more EA to get to those products than the products have to use to get back towards the reactants. Right? So, if we increase temperature, it's going to have a greater effect on the forward rate constant than on the reverse rate constant. And so because it has a greater effect on the forward, because the forward has so much more heat that it needs to take in than the reverse reaction, so increasing the temperature is going to have a larger effect. So that means if your forward reaction gains in value, that increases your Kc value as your temperature increases. Oh my gosh, sorry. So what if we have a reverse reaction? Sorry, an exothermic reaction. So that means reactants to products. So that means in an exo reaction, the EA of the forward is less than the EA of the reverse, right? So if we increase temperature, you're going to affect the reverse rate constant, which means then you're going to decrease that Kc value. And so it's just, again, understanding what temperature effect temperature has on both rate and on the Kc. And remembering, increasing temperature always affects endo, decreasing temperature always affects exo.